The most dangerous thing about the rocket hitting the moon tomorrow is not the rocket. For 18 months, a spent Falcon 9 upper stage has been circling in a lopsided orbit nobody was watching, because the radar that guards our sky goes blind at lunar distance. Tomorrow morning it arrives at 5,400 miles an hour and lifts more than 1,000 tons of the surface into a sky with no air in it. Whether any of that can reach Earth has a precise, checkable answer. This is the story of that answer and of the sentence in a Los Alamos paper that makes it worse. Sometime around 35 minutes past 6 in the morning, Universal Time, on the 5th of August, a dead machine built by human beings will hit the moon. We know the hour, we know the minute, we know the second. To within a few seconds either way, we know the patch of ground, a heavily cratered stretch near a crater called Einstein, close to the western edge of the moon as we see it from Earth on the sunlit side. For most of the people watching this, it happens in the small hours of the night, 2:35 in the morning on the American East Coast. There is nothing to switch off, nobody to call, no thruster to fire. The object has no engine, no radio, no name, and no owner willing to claim it. It has a catalogue number, and it has a velocity, and the velocity is 5,400 miles an hour. That is 2.43 kilometres a second, 8,700 kilometres an hour. If the moon had air, that would be roughly 7 times the speed of sound. And because the number is large and the target is the object that raises our tides and lights our nights, the question people keep asking is the obvious one. Is that dangerous? Not poetically dangerous. Actually dangerous to us down here, 385,000 kilometers away. The answer is not the one most people expect in either direction. And to get to it honestly, we have to start with what is actually falling. The object is the spent second stage of a SpaceX Falcon 9 rocket. Its only formal identity is a catalogue designation, 2025-010D. That string tells you almost everything about how little anyone cared. It was the 10th orbital launch of 2025, and the 4th piece of hardware from that launch that anyone bothered to track. It flew on the 15th of January, 2025, and it did its job perfectly. It carried 2 commercial landers away from Earth and toward the moon. One was Blue Ghost Mission 1, built by Firefly Aerospace, which touched down successfully on the 2nd of March, 2025. The other was Resilience, the second Hakuto R lander from the Japanese company iSpace, which lost contact roughly 90 seconds before touchdown on the 5th of June and crashed. A 4th object, the canister that held the 2 landers together, stayed in orbit for 2 months and then burned in over the border between Argentina and Chile. The upper stage did not come home. It was left in a lopsided orbit around Earth with a period of about 26 days, swinging in to around 220,000 kilometers and back out past 500,000. The moon sits at 385,000. Those 2 paths cross. For 18 months, the stage and the moon arrived at the crossing point at different times. On the 5th of August, they arrived together. It is 12 meters long and 4 meters across, about the height of a 5-story building, tumbling end over end in the dark. Its mass is genuinely uncertain, somewhere between roughly 3,900 and 4,900 kilograms, because nobody knows exactly how much propellant is still sloshing inside it. That uncertainty is going to matter later. Here is the part that reframes everything else. Nobody was tracking this object, not in the way you are imagining. The United States military maintains the most capable space surveillance network on Earth, and it works by radar, and radar is useless at this range. Radar signal strength falls off as the 4th power of distance. The moon is roughly 400 times farther away than the satellites in low orbit, which means a return from out there is more than 25 billion times fainter. The same network that has tracked gloves and tool bags dropped by astronauts cannot see a 5-story rocket stage at lunar distance. What saw it were telescopes, specifically the asteroid surveys, instruments whose actual job is finding rocks that might hit us, and which pick up high-orbiting junk, whether they want to or not. along with amateur astronomers running serious equipment from their own back gardens. Observers in Mississippi, in Utah, in Beijing, and in England. And the man who turned those points of light into a prediction was Bill Gray, working alone at Project Pluto with orbit determination software he wrote himself. In September of 2025, Gray's code looked at the accumulated observations and returned an impact with the Moon on the 5th of August 2026. By late February of this year, the solution rested on 1,053 separate observations. The impact was not announced by an agency. It was found by a private individual and published on his own website, and it will not hold still. The dominant uncertainty is not gravity. We know gravity to absurd precision. It is sunlight. Photons landing on a tumbling metal cylinder push it, very gently, in a direction that changes as it turns. Grant Privet, an observer in the United Kingdom, caught the stage brightening and fading 5 times in a single 12-minute exposure. Jean-François Gu measured its light curve over 3 minutes. That is a body spinning in the dark, catching sun on different faces, which is why the prediction moved. In June, it shifted 9 minutes earlier and 170 kilometres to the northwest. In July, it moved again. It moved again on the 1st of August. We know this collision is coming. We are still, this week, arguing with sunlight about exactly where. So what happens when it lands? The kinetic energy is about 12 billion joules. Gray's translation into human scale is useful. Roughly the energy of 3 tons of TNT, or about 15,000 sticks of dynamite, released in a fraction of a second in a place with no air to carry the pressure wave. The crater will be small. The team led by Benjamin Fernando at Los Alamos National Laboratory expects a final diameter of 20 to 30 meters, with the standard scaling relations landing near 27 meters across and about 5 meters deep. Gray's independent estimate is smaller still, around 17. Call it a basketball court, gouged out to roughly chest depth at the rim. You will not see it from Earth. No telescope on this planet can resolve it. Only a spacecraft in orbit around the Moon can find it, and only afterward. There is a real possibility of 2 craters instead of 1. When the Chinese rocket stage hit the far side in 2022, it left a pair, one about 18 meters wide, one about 16, which is generally read as a heavy engine at one end and an undeclared mass near the top, arriving as separate impactors. Whether this stage is decapitated in the same way depends on which way it happens to be pointing in its final second. For a tumbling object, that is not something anyone can predict. But the crater is not the interesting number. The interesting number is what comes out of it. The Los Alamos simulation puts the excavated mass at roughly 1,100 tons of lunar regolith. The classical scaling relation independently gives about 1,200. Both say the same thing. This object will throw between 150 and 200 times its own mass off the surface of the Moon. A 4-ton machine lifts more than 1,000 tons of the Moon and throws it, which raises the only question that actually matters. Throws it where? Here is where the honest answer arrives, and it is not the frightening one. The fastest fragments coming out of that crater are modelled at around 1,200 meters a second. The escape velocity of the Moon, the speed something must reach to leave permanently, is about 2,380 meters a second. The fastest thing this impact can produce is moving at roughly half the speed it would need to get away. Nothing leaves. Every gram of what the collision lifts is on a ballistic path that ends back on the lunar surface. In the Los Alamos model, about half the tracked particles have already fallen back within 5 seconds. Only about 2% are still in flight after 30 seconds. The finest dust may hang for 10 minutes before it settles, and then it settles. There is no mechanism, none, by which material from this impact reaches Earth. Not a fragment, not a grain. The Moon is 385,000 kilometers away, and the debris cannot get past the first few kilometers of its own sky. Gray, who found the thing, says as much himself. He calls the impact a matter of probably minor scientific interest, notes that it presents no danger to anyone, and adds that if it worries you at all, you should be considerably more worried about the many similar objects that miss the moon entirely and come down here instead. So that is the answer to the title question, stated flat, with no hedging. This collision cannot hurt you. Now hold that thought, because there is a sentence in the Los Alamos paper that we have not read yet. But first, stand there for a moment, because the strangest thing about this event is how quiet it is. Put yourself on high ground a few kilometres from the impact point, near the crater Einstein. The sun is up. The sky above you is black anyway. No air, no scattering, no blue. You are near the edge of the visible face, so Earth sits low and enormous on your horizon, a blue-white shape that never rises and never sets. You will not hear it coming. There is nothing to carry sound. You will not see a streak because there is no atmosphere to make one glow. The stage falls out of the black in complete silence, and for you, it does not exist at all until the instant it stops existing. Then the ground under your boots moves. A flash, bright or barely there, nobody can say, and a column of pulverized rock climbing straight up into a sky that gives it nothing to push against. On Earth, a plume like that would billow and slow and drift. Here it does not. It rises as a clean geometric curtain, every grain on its own precise ballistic arc, indifferent to every other grain. Some of it climbs kilometres. And then, in a silence you cannot imagine, because you have never been anywhere without air, it all comes down, not drifting, falling at exactly the speed it left, hammering the surface for 1,000 square kilometres around you. That is the part the models care about. That is the part that has a number attached to it. The Fernando paper is a technical document about telescope scheduling and ejector physics. Buried in it is one sentence that changes the shape of this story. The maximum ballistic range of resolved particles is found to be slightly under 1,000 kilometres, which is far enough to be significant from the perspective of presenting a hazard to future astronauts or infrastructure across much of the lunar surface. Read that again. Not a hazard to Earth, a hazard in principle, spanning 1,000 kilometres of the Moon, roughly the distance from London to Warsaw, from one abandoned fuel tank. And it is worth being precise about why the vacuum makes this different. On Earth, a fragment thrown 1,000 kilometres is a fantasy. The air would strip its energy away in seconds. On the Moon, there is nothing to slow anything down. A rock leaves the crater at whatever speed the physics gives it, travels the entire arc at that speed, and arrives at the far end still carrying it. There is no weather afterward either. Whatever lands stays exactly where it lands for geological time. There is a further complication that the same team flags. Rocket stages are not inert rocks. Their words, any unspent fuel in a stage may explode on impact, releasing more energy than a natural object of the same momentum would. Nobody knows how much propellant is left in this one. That is precisely why the published mass estimates disagree by 1,000 kilograms. Gray addresses the risk directly and does not inflate it. Some of that shrapnel could, conceivably, go flying and hit one of the Chinese landers on the surface. He calls it very long odds against, notes that none of them are anywhere near this spot, and says he does not think it meaningfully raises the risk of being on the Moon. Then he adds the line that matters. If we have humans on the Moon in the coming years, we might start to worry more about this sort of thing. But it won't be a problem on the 5th of August, except there is one spacecraft for which that reassurance is thinner than anyone intended. Danuri is South Korea's first mission beyond Earth orbit, the Korea Pathfinder lunar orbiter, operated by the Korea Aerospace Research Institute. According to the Fernando paper, immediately before the impact, the derelict upper stage will pass Danuri at a distance described as, quote, on the order of a few kilometres or less. That conjunction happens approximately 2 minutes before the stage hits the ground. Sit with the numbers in that sentence. 2 minutes, a few kilometres or less. between a functioning national science spacecraft and an untracked 4-ton tumbling object whose predicted position has been revised 3 times this summer, by margins measured in kilometres, because sunlight keeps pushing it around. Nobody scheduled that encounter. Nobody could have prevented it, because avoiding something requires knowing where it is with a precision nobody has out there. And the only reason anyone on Earth knows the encounter is happening at all is that one man ran the orbit on his own software and posted the answer publicly. Danuri's operators have taken baseline images of the impact region and plan follow-up observations as close to real time as they can manage. The spacecraft is expected to be entirely fine, and it almost certainly will be. But expected to be fine and safe are not the same sentence. One of them describes a system with margins. The other describes a coincidence that happened to land on the right side of the odds. We got a warning shot this week, and we got it by luck from a hobbyist's software. Which raises an uncomfortable follow-up. How much of what we think we know about this impact is actually measured? Almost none of it. And that is the second story hiding inside the first. Consider the flash. The Fernando team models its brightness across a range from magnitude 3 at the bright end, comfortably visible in a modest telescope, down to fainter than magnitude 15, which is to say invisible to essentially everyone. That is a spread of roughly 100,000 in brightness, and it turns almost entirely on whether the stage happens to hit loose powder or exposed bedrock. The impact ellipse contains both. Then there is this. No natural or artificial impact flash has ever been detected on the sunlit portion of the moon, not once, and across the entire history of things, humans have deliberately or accidentally crashed into the moon. Luna 2 in 1959, Highton, Smart 1, Kaguya, L Cross. No actual measurement of the flash brightness from an artificial lunar impact has ever been published. Not one usable data point in 67 years. The plume estimates fare no better. William Joe and colleagues at the University of Texas at Austin model an ejector curtain reaching 15 to 20 kilometres, with a central spike climbing to between 75 and 100 kilometres, and spreading 183 kilometres sideways. Bright enough, they calculate, to stand out against the black sky for the first few minutes. The Los Alamos simulation, which deliberately resolves only fragments larger than about 1/3 of a metre, tracks its highest particles to around 1.5 kilometres, while acknowledging the finer material almost certainly goes higher. Joe is candid about it. His calculations, he says, suggest the plume should be several orders of magnitude brighter than the dark sky background for the first few minutes. But he stresses that this is a single nominal case, that the real event will look different, and that his numbers are on the optimistic side. His actual worry is that observers will fixate on a flash that may last less than a second and never track the ejector, which is where the science is. When NASA deliberately crashed a Centaur stage into the lunar South Pole in 2009, under conditions chosen to be as favourable as possible, ground-based observatories reported uniform non-detections. The plume was only recovered years later by reprocessing the data. So every hazard number in this story, the crater size, the 1,100 tons, the 1,000-kilometre range, is the output of models that have never once been graded against a real artificial impact on the moon. That is the actual reason 2 research teams, several major observatories, and a citizen science network are all pointing at the same patch of ground at 2:35 in the morning. And this is where the real answer to the question lives. The reason none of this mattered in 1972 is that there was nothing up there to damage. Apollo crews deliberately crashed their own spent stages into the moon between 1969 and 1972 as calibrated shocks for the seismometers they had left behind. It was good science on an empty world. The world is not empty now. In lunar orbit today, NASA's Lunar Reconnaissance Orbiter, 17 years into a mission that keeps getting extended, India's Chandrayaan-2 orbiter, South Korea's Danuri, China's Queqiao relay satellites, one of them in a halo orbit beyond the far side. NASA's capstone. On the surface, China's Chang'e 4 lander and its Yutu-2 rover are still working, and experts estimate there are only a few dozen pieces of derelict hardware in cislunar space right now. But they also say astronomers have very little idea where most of those pieces are, what they are, or how they got there. There is no catalogue out there comparable to the one we keep for low Earth orbit. There is no traffic management regime at all. Coordination is done by ad hoc agreements and waivers, which several published analyses describe, bluntly, as unsustainable. Meanwhile, more than 30 countries are planning over 100 lunar landing missions in the next decade. The human timeline is no longer hypothetical either. Artemis 2 launched on the 1st of April this year and came home on the 10th, carrying Reed Wiseman, Victor Glover, Christina Koch and Jeremy Hansen around the far side of the Moon, the first crew to make that trip in more than half a century. Artemis 3 is targeted for the middle of next year. The crewed landing has slipped to Artemis 4, no earlier than 2028. A permanent base is the stated goal beyond that. Fernando and colleagues do not hedge about the direction of travel. They write about the multimodal hazards posed to future lunar infrastructure and astronauts from space debris hitting the Moon, and about the need to avoid uncontrolled increases in debris in lunar orbit, as is the case now in low Earth orbit. That last clause is a warning delivered as a comparison. There is one more turn, and it is the one that should stay with you. This object is hitting the Moon precisely because it did not hit us. Over 600 Falcon 9 rockets have flown, and almost none of their upper stages could ever do this. Only lunar-class missions carry hardware far enough out to end up on a moon-crossing path. The rest come down here, and they come down here constantly. Objects heavier than a metric ton are now re-entering Earth's atmosphere at a rate of roughly once a week. Between 20 and 40% of an abandoned rocket body's mass typically survives the fall and reaches the ground intact. In May of 2020, an 18-ton Chinese core stage came down uncontrolled and dropped debris, including a 12-metre length of pipe, onto 2 villages in Côte d'Ivoire, damaging buildings. An analysis backed by the Federal Aviation Administration projected that on current trends, debris from a single satellite constellation could cause an injury or a death about once every 2 years by 2035. And here is the part I find hardest to sit with. The fix already exists and is already in use. When the James Webb Space Telescope launched, its upper stage was deliberately placed into an orbit around the Sun on a path calculated to miss us for at least a century, and probably for thousands of years. In November of 2025, the upper stage from the Escapade launch was disposed of the same way. China's recent lunar launches have done it too. The technique is solved, it is simply not required. So, is the rocket about to slam into the Moon a threat to Earth? No, not remotely. Nothing it lifts off that surface is fast enough to leave. And the honest answer to the question in the title is a flat and unqualified no. But that was always the wrong question. The threat was never pointed at us. It is pointed at the place we are currently spending hundreds of billions of dollars to occupy. A world where a 1,000-ton spray of rock travels 1,000 kilometres without slowing down, where nothing ever erodes, where a spacecraft can be missed by a few kilometres with 2 minutes to spare, and nobody finds out until an amateur's software says so. On the 5th of August, at 35 minutes past 6 in the morning, we will put a crater on the Moon by accident, in front of every telescope we can point at it. We should watch it very carefully. Because we are about to start living there, and this is the last time an impact like this one will be harmless. Thanks for watching, and I'll see you in the next one.